In this screencast, I want to talk about the general approach that we use to determine the time complexity of an algorithm. We're going to follow a 5-step process here, and the slide just shows those 5 steps. The first step is determine how big the problem is. This is basically a measure of how much space it takes in the computer to define the problem, or equivalently, how much space it takes to read in the problem. We'll talk about this a lot more later on. For right now, we'll just assume that we can determine that fairly easily. And you'll see for the algorithms I'm going to give examples of, it is easy to see what it is. Then we're going to identify the basic operation. That's going to be the operation or the instruction in the algorithm that generally determines the overall performance of the algorithm. So typically it'll be an instruction that gets executed frequently and is likely to be taking up the most of the time. So it may be a more complex operation than just, for instance, incrementing a loop. That's typically not considered a basic operation. The next step is to determine whether the order or the way the input is presented to the algorithm impacts how long the algorithm is going to take, or equivalently, the number of times the basic operation will get executed. So for example, for sorting routines, for some sorting algorithms, if the elements are already sorted, then they'll run very quickly. If they're in reverse sorted order, then they'll run very slowly. Insertion sort is an example of that. So in that case, you have to decide whether you're going to determine the number of operations for the worst case, the average case, or the best case. And normally for us, it will be the worst case. After all, that's what usually concerns us is what's the longest time somebody's going to have to wait for a result. The next thing is to basically determine the number of times the basic operation is going to get executed. And for iterative algorithms, that typically will be a summation of a bunch of numbers. And for a recursive algorithm, it's going to be a recurrence relation. And neither one of those is very helpful in terms of being able to compare the number of operations for one algorithm compared to another algorithm. So the next step is develop what's called a closed form solution, and that is basically just to get a simple formula that tells you the number of instructions that have to be executed. And you will see how to do that both for iterative and for recursive programs. So the first example I want to do is selection sort. Let me remind you how selection sort works. You look at a list or an array of elements, and you go through the list and find the smallest one and put that in the initial position. And then look through the remaining elements, get the smallest element in those remaining elements, and then put that in the next position. So in other words, we're sorting in ascending order. We find the smallest element in the whole list, put that in the beginning, and then take the next smallest element out of the remaining elements and put that at the beginning, etc. And you can see, this is the pseudocode. You can see that basically this is the outer, and the number of comparisons we still need to determine in the closed form solution. We still need to be determined. So now let's look a little closer at this inner loop and see how many comparisons are going to need to be done. So the first sort of situation is I equals 0, and if I is equal to 0, then the inner loop is going to go, j will go from 1 up to n minus 1, and that'll be the number of comparisons. Similarly, when I is equal to 1, then this will be 2, and it'll go from 2 to n minus 1, and so then this would be 2 to n minus 1, and so now it would be n minus 2 comparisons. So this slide shows that in gory detail. Again, each time through the outer loop, I will get incremented. So this will go up by 1 each time, and that means there'll be one less comparison in here. And so we end up with is when I is equal to 0, again, j will go from 1 to n minus 1, so we get n minus 1 comparisons. When I is equal to 1, j goes from 2 to n minus 1, so n minus 2 comparisons. And finally, when I is equal to n minus 2, j goes from n minus 1 to n minus 1, and so we have one comparison. So we just add all those up, and we get the summation from 1 to n minus 1, and that's an arithmetic progression, and the formula for that is n minus 1, the last entry, times one more, n over 2. So what we get is 1/2 times n squared minus n. So notice what we've determined. Basically, we've determined that selection sort is an n squared, ignoring all the constants in this lower order term. It's going to be an n squared, we have n squared performance. That's the number of operations that it's going to need to execute. And it doesn't depend on best, worst, or average case, because we're going to have to find the min by searching through the list every time. So we're going to have to search through the remaining elements of the list every time. So we always get these number of comparisons. Okay, so now we'll do a more interesting example. We'll go ahead and look at insertion sort. So insertion sort now works differently. It takes the array, okay, and what it strives to do is basically get just the first few elements sorted, and then it just looks at the next element here like this. So assume these are all sorted, looks at the next element, and then determines where it goes in there. So in other words, these are in sorted order, so there'll be some group of them that are bigger than x, and then some group of them that are less than or equal to x. And so we'll put it right there. And that grows the sorted part of the list by one element. And so we just keep doing that every time. Okay, so again, our problem size is going to be the number of elements to be compared. The basic operation will be comparison. But now the best case and the worst case are going to be different. Because if it's already sorted, then notice you're only going to have, how this works, you're only going to have to compare x with this first element. You'll realize that x is greater than that element, and so you're done. That's tested here in the while loop. So once aj minus 1, you only stay in this while loop if aj minus 1 is greater than aj. Otherwise, you just drop right out. On the other hand, if it's in reverse sorted order, in other words, the biggest element is here, okay, so suppose it looks like this, 10, 8, 6, ... Then you'll start out in the 10 will be in sorted order, and the 8 will have to be swapped, so you have to move, do a comparison, and then do a move, first time through the loop, and then you'd have 8, 10, 6, and now 6 will have to compare with the 10. It's smaller. Then you'll have to compare it again with the 8. Okay, and then finally get 6, 8, 10. So you can see if the elements are in reverse sorted order, the number of comparisons you have to do goes up by 1 each time. And so then what you'll get is that the total complexity is going to look like this: 1 plus 2 plus 3 up to n minus 1. So that's written down a little bit more carefully on this slide. So again, problem size is the number of elements times the storage needed for each element. Basic operations comparison, best and worst cases are different. Again, best cases when they're already in sorted order, worst cases when they're reverse sorted order. The best case only requires n minus 1 comparisons altogether, but the worst case requires the same summation that we had for selection sort. So the closed form solution for the worst case is the same as selection sort, but for the best case, it's just n minus 1. So these were a couple of simple examples for determining the formula for how many times some basic operation is going to have to get executed. Again, we looked at an example of sorting, which is relatively straightforward. The one important takeaway here is that in looking at the loops, when they're nested loops, you want to generally start with fixing the indices from the outer loops to whatever their initial numbers are, and then looking at how many times the innermost loop is going to execute, and then vary those numbers to get the summation of the inner loop, and see how, and then once you've got that, then you work your way out from the inside out. Typically that's kind of the best way when you're beginning, when you're doing this for the first few times. Good luck, I hope that's helpful, and see you on the next screencast.